Hey everybody, we are back. Let's talk about section 1.4, polynomial functions and rate of change. So we've learned linear, we've learned quadratic, but let's talk about polynomials. This means many different types of terms, specifically more than linear and quadratic. A linear function is x to the 1, this is linear. A quadratic function is x squared. So anything past that, x cubed would be cubic, and anything past that we call polynomial. So a polynomial means we have many terms, and it just means that whatever's here, this is our highest, what we call degree or exponent, and this coefficient is also called the leading coefficient, but specifically it's a coefficient, which is the number in front of the variable. And when it's the highest degree, we call this the leading coefficient, meaning the coefficient on the highest degree. We also see here the rest of these exponents are always in decreasing or descending order. So it's a decreasing order of the exponents. And all of these are coefficients, but they're just not leading coefficients because it's not on the highest exponent, okay? So if n is the positive integer and it's the highest, then each one below it goes down by 1. So this could be, let's say, if the highest one was 10, this could be 9, this could be 8, and so on all the way to the second, the first. And then this is called the constant term, aka has an x to the 0 in it, but we just call it the constant term. So for example, if I said you could have like 7x to the 5th minus 3x squared plus 6x minus 2. Let's say that's your polynomial, okay? The leading term of our standard form here is the full a sub n of x to the nth power. In our example, the leading term would be all of this. So for example, this would be 7x to the 5th, okay? In our standard term, the polynomial will have a degree, which is the highest exponent. So this would be n, aka the highest exponent, okay? And by example, that would be our highest exponent here. Let me see if I could find it. It's right here at 5, okay? And the leading coefficient is the coefficient right in front. So on our standard example, that would be a sub n, which just means a value in front. And then for our example, it would be 7, okay? So example from above, let's say degree of the polynomial. We already know the degree is the highest exponent, that's 5, and the leading coefficient is the coefficient on the highest variable, which is 7. So sometimes the polynomial is not written in standard form, meaning it's not in descending order. So you might have to look at them and put it in descending order. So let's say we look at this function f of x, okay? Let's go ahead and write this so it's in descending order. We're going to rewrite this in standard form, which is in descending order. So that would be like f of x equals negative 2x to the 6th. Don't forget that negative in front of it. And then the next one would be positive 14x squared, and then positive 6x, and then plus 1. So again, we're going in descending order. So the degree here would be the highest exponent, which we see is 6. And the leading coefficient is the coefficient in front of that term, which is negative 2. While the leading term would be all of negative 2x to the 6th. Okay, so now let's talk about what's a local relative extrema, maxima, or minima. So let's say, for example, we had like some kind of, curvy function here, something like this, okay? So here's what a local or relative extrema, okay? So a local or relative maximum, okay, happens when we go from increasing to decreasing. So if I look here at this, I see that we're going from increasing here to decreasing here. So this tells me that this right here is a relative maximum, or we could call that a local maximum. We also see that we're going from increasing here to decreasing here. So also this makes this also a relative maximum, okay? Let's say I was looking for a local, something from decreasing to increasing. That would be a local or relative minimum. So if I'm looking for something that's going from decreasing to increasing here, that point at the bottom in between where it goes from decreasing to increasing is a relative minimum. Okay, so we see that here. We also see this here. Okay, so an included endpoint, so here we can see this doesn't go forever. We have an included endpoint here and here. A polynomial with restricted domain may also have a local or relative extrema. Here's what that means. Just like we have local maximum or local minimums, as long as it's the lowest point, this is also a relative minimum because in that region it's the lowest point, as well as this one, where this is still a relative maximum because it's the highest point in that area. All right, let's turn the page. Let's talk about global or absolute extrema, which is an absolute maxima or a minimum, okay? So if we're talking about this, all of the local maxima, or out of all of them, the greatest of them is called the global or absolute maximum. Out of all of the local minima, the least one is called the global or absolute minimum. So let's say you have a series of a bunch. So like this, let's say you have a function that looks like this. Okay. I see we have a bunch of local maximums. One's here, one's here, one's here, right? Our greatest local maximum is going to be the absolute maximum. Let's say, and actually, let's take this off real quick. No arrows here. Whoops. Back up. Here we go. Let's say there's none of this. Okay. Let's put a dot here. Let's put a dot here. So our greatest maximum, actually this is a maximum as well. Our greatest maximum is going to be this one because it's the highest out of all of the maximums. So even though this one is the absolute maximum, and then all of these are also relative maximums because they're the highest point in the region. Same thing goes for if we're looking for minimum. So I see a local minimum here, 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 and here, okay? Out of these local or relative minimums, the lowest one is right here. So we call this an absolute minimum. Okay, so let's try this. It says in this example here, find the extrema, maximums or minimums, and where they occur. If there are none, right? None. So let's look for an absolute minimum. So it's the lowest possible point. We see this here. We call this point -6, -2. So the minimum is always the y value. So this is a minimum of -2 when x is -6, because the highest and the lowest values are talking about the y values, the vertical height or the vertical low. Okay, we're not talking about a minimum or maximum happening at an x value. So we say the minimum is the y value when the x is, and then we say what the input for the x is. Is there an absolute maximum here? Well, we know from here, it goes here, here's our tallest, and then here it goes forever. So are we ever gonna actually get to the tallest? We're not. So in this case, we'd say that there's none. Okay, what's a relative minimum? So a relative minimum is going to be areas where we have a low point. So we see low points here, we see a low point here, and we also see a low point here. So you're gonna list where do we see those values of x at those low points. So this is where value of x is 6, where this is 3, and where this is 2. So we'd say -6, -3, and +2. And then where do we see relative maximums? Let's look for that. Relative maximums are here, here. And even though this goes on forever and it's a maximum, it's not a relative maximum. This goes on forever. So we say our relative maximums happen where at this point where x is -4 and at this point where x is 1. So we say when x is -4 and 1. All right, let's talk about what happens in between two zeros. So this idea that if you've got two zeros, they happen on the x-axis, what's got to happen in between them if it's a continuous function? So if we have two zeros of a polynomial or a non-constant polynomial, then there must be at least one local extrema between those two zeros. And here's what this means. So we're going to do a couple examples here. So use some different colors for this. Let's say we have one function where it goes from below and it's increasing. The only way I can take this function through the other zero is if it starts to decrease and then go this way. Okay. There are other ways you could achieve this as well. Let's say you were going from decreasing through that zero. The only way to get back through it would be start increasing again and go through there. We could also have something that looks like kind of crazy, where we have a function that goes through the zero and it can increase and decrease a lot and then still go through there. So there's a couple of different things that can be happening, but there has to be at least one local extreme, right? And we see that here, 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 and here, right? Depending on which case we're talking about. All right, let's look at this next part. If let f be any polynomial function where we have this value, f of -2 is 0, f of 0 is 5, f of 4 is 0, and f of 7 is -1. So are there any guaranteed extrema? So what are we talking about here? We just talked about before how if there's two zeros, we can guarantee there's at least one maximum or minimum. So do we see any zeros here? Well, I see, hey, this is a 0, and this is also a 0. What I see here, is this a 0? No, but when x is 0, the y is 5. So we call this a y-intercept, okay? So if I were going to kind of sketch this, this is what it's looking like. When f is -2, there's a 0. When f is 4, there's a 0. When x is 0, y is 5. Let's say it's here. And when f is 7, y is -1. So it looks something like this. So what I can see is, in order for this to work, I can see this goes through it, but in order for it to go through this as well, it's going to kind of curve through here. That's going to go below, right? So we have to know there has to be at least one extreme. That's going to be somewhere about right here. So we say yes. There must be at least one extrema on the interval between -2 and 4. We can also call this the interval from -2 to 4 in interval notation, okay? All right, let's talk about even degrees. So if the polynomial has an even degree, even numbers are like 2, 4, 6, 8, and so on, there is either an absolute maximum or an absolute minimum, okay? If it's a positive leading coefficient, meaning positive 6 in front of that as a coefficient, you'll have an absolute minimum. And this is because if it's positive and even, it will look something like this, right? This could be something like 6x squared, for example. This means that it has to have a lowest value, okay? If it has a negative leading coefficient, meaning like if you have a negative, I don't know, 3x squared, it's going to look like this, something. That means it has to have an absolute maximum. Okay. Last page. If there's is there an absolute maximum or minimum for each function? Let's see. So we've got it positive and even degree. If it's positive and even, this tells me yes, there is a minimum. This we have a negative and even, so negative and even, which also tells me yes, there has to be a maximum. Here we have a positive odd. So if that odd tells me, actually, no, we won't have an absolute minimum or a maximum. So odd degrees mean that we do not have an absolute, I can't write, absolute extrema. An example of this would be like if this was 6x to the third, it would look something like this. It goes forever in both directions, which means it can't be the highest or the lowest. Last part, let's talk about the point of inflection. We've already talked about this quite a bit in the first section. But if let's say I've got something, this is concave, let's say down here, and I continued it, so it's symmetrical, and this is concave up, and then this is concave down again. We see this here. So we know these are points of inflection where the concavity changes and where the average rate or the rate of change changes from increasing to decreasing or decreasing to increasing as well. So remember, we look for a concave up, looks like a cup, and concave down looks like a frown. All right, that's it for now. I'll see you next class.